Hello and welcome. In this video, we're going to take a look at a little bit more of an expanded view of what we mean by the derivative of a function. Now, we've seen derivatives of functions and partial derivatives of functions, and we've seen the gradient of a multivariable function before. But we're going to keep expanding that differential calculus to include fields and vector functions. So really what we should be doing at this point in time is introducing a standard vector differential operator. The vector differential operator, we can refer to this as nabla, or sometimes referred to as del, depending on the kind of context, is really just a vector consisting of partial differential operators. In R3, that would be partial x, comma, partial y, comma, partial z. Now we've seen this before when we looked at the gradient of a function, and that was to do with scalar functions. So that'd be the first example of where you may have seen this symbol before. And we've seen the notation nabla f, but sometimes we've just referred to it as gradient of f. Now, if you want to start thinking about this as actually being a vector differential operator, then it really starts to make sense that this is like scalar multiplication. Multiplying by a scalar function, we'll end up with the partial derivatives. Partial f with respect to x, partial f with respect to y, partial f with respect to z. Now remember, the gradient is useful for many purposes. It's used to find the directional derivative of f in the direction of a unit vector. The directional derivative of f in the direction of a unit vector u hat is the gradient of f, or nabla f, dot product with the unit vector u. Now, one way you can interpret the gradient of a scalar valued function is it is giving us a direction of the greatest rate of change of f. We can show that the gradient of f points in the direction of the greatest rate of change of f by thinking about taking a point, let's say x, y, z, and let's suppose the gradient points in the direction of this vector I've drawn here. Now, let's suppose that we choose a direction for our direction vector u hat. Well, using the alternate form of a dot product, the value of the gradient of f dot u hat is equal to the magnitude of the gradient of f times the magnitude of the unit vector times cosine theta, where theta is the angle between the two vectors from 0 to pi. Well, because this is a unit vector, the magnitude of u hat is equal to 1. And if we want this to be the largest value possible, we would need to make cosine theta as large as possible, and that's only going to happen when we make cosine theta equal to 1 or theta equal to 0. Well, that tells us that the largest directional derivative happens when u is parallel to the gradient. So we can really imagine, again, gradient of a scalar valued function is a vector pointing in the direction of the greatest rate of change of f. And this interpretation will extend to more than just 3 dimensions. It's just easier to imagine this in either 2 or 3 dimensions visually. But in general, in n-dimensional space, the gradient of f is a vector that points in the direction of the greatest rate of change of f at every point p in the domain of f. So this is interesting. The gradient of f takes a scalar function as its input, and its output is a vector. So this is going to be a vector valued function. And we've already seen that a gradient field is, in fact, a conservative vector field. All right, now what happens if we use nabla, or the vector differential operator, on a vector field? Well, that wouldn't be scalar multiplication now. We would have to figure out what kind of multiplication to use. We could either use a Cartesian product or cross product, or we could use the scalar product or dot product. Well, both of those would have interpretations as well. If we use the Cartesian product of the vector differential operator nabla cross f, our vector field, what we get is called the curl of a vector field. Well, let's take a look at what that would look like explicitly in the case of a vector field in 3 dimensions. For a vector field f of x, y, z, let's suppose that the components are p, q, and r. Then calculating the curl can be done using a 3x3 determinant. This gives us curl of f equal to the partial r with respect to y minus partial q with respect to z, comma, partial p with respect to z minus partial r with respect to x, comma, partial q with respect to x minus partial p with respect to y. it is a little bit tough to maybe interpret curl immediately in 3 dimensions, so let's start off with 2 dimensions. If we have a vector field in 2 dimensions, let's say we have just pi plus qj. Well, we can still calculate curl by picturing this as a vector field in 3 dimensions with our r component equal to 0. Now, since r is equal to 0, and the partial derivatives of p and q with respect to z would also be 0, that leaves us with 0, 0 for our first 2 components of curl. And then we have the partial derivative of q with respect to x minus the partial derivative of p with respect to y. And you'll see that that maybe looks familiar. That one component there is also what we've seen in Green's theorem for line integrals that exist on the xy plane. Now that we've got this general formula for curl of a 2-dimensional vector field, let's try a few quick examples and see if we can interpret what curl means. Here I've got an example of 4 vector fields, x, y, negative x, negative y, y, negative x, and negative y, x. And if we're calculating curl of a plane vector field like this, we know that it's either going to be pointing in the positive z or negative z axis, or perhaps curl is equal to 0. Let's try each of these calculations out. In our first example, the curl of x, y is going to be partial y with respect to x minus partial x with respect to y, and both of those are 0. So our curl is 0, 0, 0. That's just simply the 0 vector. And very similarly, in our second example, calculating curl of f is going to be also equal to 0. The partial derivative of negative y with respect to x is 0, minus the partial derivative of negative x with respect to y, that's also 0. But moving on to these other 2 examples, we have y's and x's in opposite components. So calculating the curl of y, negative x, we will have partial negative x with respect to x minus partial y with respect to y. That'll be negative 1 minus 1, which is negative 2. So our vector for curl is 0, 0, negative 2, or simply negative 2 times k. And what about this last example? The only change here is negating the vector field, negative y, x. So it would make a lot of sense here when we calculate curl that we end up again with just 2, but this time positive 2k. Okay, well, maybe this helps you to visualize what curl means in a 2-dimensional sense. At any point here, you can see that treating this vector field as if it was a velocity field, perhaps of some sort of fluid. This would be like a point here where a particle would be traveling in the direction of the arrow. And you can see that at any point in time, it looks like our fluid is essentially traveling outward and speeding up away from the origin. Whereas in examples where curl was not equal to 0, we can see that the general flow of fluid is traveling in a circular path here about the origin. Hopefully that kind of makes a little bit of sense about what curl means. Curl being this idea of rotation. But that's not simply around the origin. Let's pick any point and we can see that the curl makes sense at every single point. Let's pick a point such as 1, 1 in quadrant 1. And imagine that I have a little spinner here. These are little paddles that are in the fluid. And you can see that we have much stronger fluid flow at the top of this paddle wheel, and we have weaker flow at the bottom. If that's the case, you can see that this stronger flow is probably going to be spinning my paddle in a clockwise direction. And that paddle can be placed at any other position, and we can still see the same clockwise behavior. Whereas in the case where curl equaled positive 2k, we should see that by placing a spinner at any location, we will have stronger flow away from the origin, weaker flow closer to the origin, and that will result in a counterclockwise spin. And using our right-hand rule, our clockwise direction gives us curl pointing parallel to the negative z-axis, whereas curl in this counterclockwise direction is a vector in the orientation of positive z. Again, right-hand rule, negative z or positive z gives us a clockwise or counterclockwise rotation. But in vector fields where we don't see any sort of rotation, curl is equal to 0. Now that we've seen curl in a two-dimensional sense, we can think about what curl would look like in a three-dimensional vector field. Now, I've got a Maple worksheet here that might help us to visualize that, although there's a lot of stuff going on here. The vector field I've got, you can see 3x times y plus z, 2y times x plus z, negative 3x plus y. And I'm going to take a look at curl here. You can see curl is given by the three components, 1 minus 2y, 3x plus 3, and 2y minus 3x. So, unlike in that last example, the x and y components of curl are not both 0. And we can see here in this picture that I've got my vector field. It's a little hard to see. Vector fields are always tough to visualize in 3 dimensions. But I've got a point here around the backside where I've got curl from this point here, pointing in the direction of this red vector. Now, using the right-hand rule, particles in this fluid would be rotating around that axis. And you can kind of understand the orientation using the right-hand rule here. So I'll animate this, and what I'm going to be doing here is I'll actually be taking this curl vector at that point, moving the point through the field and seeing what the curl vector looks like as it travels through the fluid. So here you can see the orientation, right-hand rule. And as I travel through the fluid, I may stop here at this point in time and see if we can just zoom in a little bit here. Okay, so at this point in time, if you're very careful looking at some of these vectors here, I have slower fluid at the top, I have faster fluid at the bottom, and that is causing this rotation here counterclockwise with respect to my curl. As I travel further through the fluid, you can see the orientation is changing slightly. At every single point in this vector field, I have a vector for curl. And it can be pointing in all kinds of directions. And let me stop here and reassess curl. And it's hard to see, but above this red vector, I have faster fluid. And below it, I may have slower fluid. And you can see which direction I am now rotating about that point. So curl has got this idea of circulating around the curl axis. Faster flow at the top, slower flow at the bottom is going to cause this circular motion around that axis. All right, well, back to the notes here. Really what we can think of as curl is this axis of rotation. Interpreting this as a velocity field of some sort of fluid, fluid around that particular point is traveling around this axis defined by curl F according to the right-hand rule. And also the magnitude of curl will tell us how quickly particles are circulating around that point. In fact, we actually say that if the curl of our vector field equals the 0 vector at a single point, then the field is irrotational at that point. All right, now that we've seen that taking the cross product of our vector differential operator nabla cross F gives us curl, what happens if we use a different form of multiplication? Let's use the dot product. What do we end up with at that point in time? Using the dot product of our nabla, or vector differential operator, and a vector field F gives us what we call the divergence of a vector field. And we'll see why it's called that in a moment. In the three-dimensional case, where F has the components P, Q, and R, this dot product is simply the partial P with respect to X plus partial Q with respect to Y plus partial R with respect to Z. In the two-dimensional case, this is simply just the partial P with respect to X plus partial Q with respect to Y, if we don't have that extra R as our Z component. Now, once we have understood what this is in 2 dimensions, it's a little easier to visualize it. Once again, I've got those same 4 two-dimensional vector fields here. Let's calculate divergence of each of these, and then maybe we can understand what divergence can be interpreted as. In this first example, the divergence of the field x comma y is the partial derivative of x with respect to x plus the partial derivative of y with respect to y. That's just 1 plus 1, which ends up being 2. Remember that when we're using the dot product, we're going to end up with a scalar value. In the second example, all we've done is negated the two components of our vector field, and so the partial derivatives are also negated, and we end up with -2. In our third example, partial derivative y with respect to x plus partial derivative -x with respect to y is simply 0 plus 0, and we have 0 divergence. And since our fourth vector field is simply the negation of our third, we again end up with the divergence equal to 0. Now, taking a look at the visualizations here and seeing these vectors actually drawn on the field, hopefully that can make some sense in terms of what we mean by the word divergence. You can see in this first case, all vectors are flowing out of the origin. So that seems like fluid is diverging away from the origin, but not just at the origin. Pick any single point in this plane. Think about a volume at that particular point. Maybe a very, very small volume, but still think about sort of the mass of fluid flowing in and out of that little volume. Well, we have a very little amount flowing in because we have slower velocity there, and we have large amounts of mass moving out of this volume because we have higher velocity moving out. So we're not going to be changing volume, but we could think about mass changing here. Lots of mass flowing out, very little mass flowing in, generally saying that the mass is diverging from this. It's kind of like saying that the density would be decreasing in this little tiny ball. That's where we get a positive value for divergence. But in the second example, regardless of whether we use the origin or we use any other point on this plane, you can see we have higher velocity fluid coming in, slow velocity fluid flowing out. Well, that is going to start accumulating more mass in each of the little volumes anywhere on the xy plane, and that is going to be a convergence of mass, or like an increase in density. So that's not divergence, that's convergence. So if we're measuring divergence, we will associate a negative divergence with this mass converging in on a volume. Now, what about these other two that have divergence equal to 0? We've seen that the best way to visualize these is maybe thinking about curl. Both of these have lots of circulation of fluid at every point on the plane. But what about this mass flowing into a volume interpretation? For divergence, you can see we have a combination of fast fluid and slow fluid flowing into this volume. We have a combination of fast fluid and slow fluid flowing out of this volume. It really all balances out. It's like this nice equilibrium that the mass flowing in and mass flowing out are equal rates, and therefore we don't have any divergence or convergence at that point. And the same thing goes in a counterclockwise direction in our fourth vector field. Fast and slow fluid moving in, fast and slow fluid moving out. As a result, we have no convergence or divergence. A divergence of 0 is like this nice equilibrium of mass flowing in and mass flowing out at the same rate. Now, these are four fairly straightforward, simple, plain vector fields. Now, it's going to be very difficult to visualize this in 3 dimensions. In fact, I don't think I'm even going to try that with an animation. But let's take a look at a little bit more interesting vector field just on the xy plane. So here in Maple, you can see I have quite an interesting looking vector field. Scrolling up here, this is the vector field sine x comma cosine y. So you can see as I travel through the xy plane here, I have areas where it looks like fluid is flowing in and out, maybe the same rate. If I have my mouse here, you can see I have fluid flowing in from the left, flowing in from the right, flowing out, going up, and flowing out, going down. That might be nicely balanced. But here on my y-axis at the point where y equals pi, you can see that in all directions fluid is flowing outward. There are also going to be places here, you can see, where all of my fluid seems to be flowing inward. So I have areas with convergence and divergence, and I have areas with almost no divergence or convergence at all. And here I'm sitting at the point 5 comma -1. That's my green point here. And I have a little animation where I've actually just drawn a path given by the function 5 cosine t plus sine t. and 5 sine t minus cosine t. This is just going to be this little point moving around in a path here, and green means divergence is positive, and red means divergence is negative, and I have convergence. So let's see this animation. You can see where I am getting divergence, almost zero, back to convergence here now. And then you can see some more convergence. Here I should be having convergence, back to divergence in this region. Once more, we'll just play that again. Look for the regions where it turns red, and you can see most of the vectors are converging, and regions where it's green, most of the vectors are diverging as we go around this path. And we get back to where we started again. So generally speaking, divergence is not just a constant. The 4 examples that we were showing here on our worksheet, well, here you can see that they are constants because I've just chosen very nice vector fields. But generally speaking, this divergence is a measurement of the fluid flow in or out at a single point anywhere in the vector field. Now we do have a word for when the divergence equals 0. This would be the scalar 0. If divergence is equal to 0, then we say that the fluid, this vector field flow, we say it's incompressible. Now that we've seen using this vector differential operator with both the Cartesian product or cross product and the scalar product or dot product, we can actually combine both of those together and form what we call the Laplacian operator. The Laplacian is an operation on a scalar function. This is where we will take the divergence of a gradient vector field. So we start off with a scalar function, we find its gradient, and then we compute the divergence. So in order, we take f, we multiply by nabla, that's just a scalar multiplication, and then we use our dot product. Now remember that the gradient of a scalar function becomes a vector valued function, but then we're taking the dot product with nabla again, and that gets us back to scalar. So this is an operation that takes a scalar function and gives us back a scalar. Now this notation of nabla dot nabla looks a little bit weird, so we just tend to write that as nabla squared. If our function is in 3 dimensions, let's say f is a function of x, y, and z, then the Laplacian of f would be just the sum of the second partial derivatives. And now it's named the Laplacian because of Laplace's equation. Laplace's equation is where we want to have this sum equal to 0. And in fact, any function that satisfies this equation where the Laplacian equals 0, we say that it is harmonic. Now, an example of harmonic functions would be functions that are simply linear in x, y, and z, because all of these second partial derivatives would equal 0. That might help you to kind of interpret what the Laplacian means. The Laplacian is kind of like an extension of curvature, this idea of concavity, but for multivariable functions. It also helps us to understand how the rate of change of f is varying around a single point. If the rate of change of f is the same all around a point, then it is harmonic. But if the rate of change differs around that point, then we're calculating the derivative of that rate of change using the Laplacian. All right, before we dive into any more theory on gradients, curl, divergence, and the Laplacian, let's just do a quick example of calculating those 4 quantities for vector and scalar functions. Now, it's important to remember what the input and output function types are going to be for these 4 derivative type of objects. The gradient acts on a scalar valued function and gives us a vector. Curl acts upon a vector valued function and defines a vector at every point. Divergent acts on a vector valued function but gives us a scalar at every point. And the Laplacian takes a scalar function, it looks at its gradient and then its divergence, and so as a result it gives us a scalar. So let's start off with a scalar function. If we start off with a function f, let's say is ln of x squared plus y squared all minus 3z. Well, we wouldn't be able to calculate curl or divergence. That wouldn't make any sense, but we could calculate its gradient and Laplacian. The partial derivatives are 2x over x squared plus y squared, 2y over x squared plus y squared, negative 3. And remember, this is a vector when we take the gradient. Well, let's take a look at a new object. Let's look at the Laplacian. For the Laplacian, we are going to take the partial derivative of the first component with respect to x, plus the partial derivative of the second component with respect to y, plus the partial derivative of the third component with respect to z. So the partial derivative of 2x over x squared plus y squared with respect to x, plus the partial derivative of 2y over x squared plus y squared with respect to y, and the partial derivative of minus 3 with respect to z, which is simply just 0. Now, we can tidy this up a little bit and simplify. Combining like terms in the numerator, we see that these two are actually just opposite signs of the same expression. And so when we add them together, the Laplacian of this function f is equal to 0. And remember, that means that our function f is harmonic. Now, why don't we take a look at curl and divergence? For those, we'll need to start off with a vector-valued function. Let's start off with a vector field, capital F of x, y, z equal x e to the y, xy squared, and ln x plus z. Now, because I have the natural logarithm of x here, I'm going to have to restrict the domain to 3 dimensions, but only for x greater than 0. Let's start off by looking at the curl. Now remember, the curl is the cross product of nabla cross f. So it's best to maybe just write this as a 3 by 3 determinant. And when we're looking at the determinant here, we can go across the top row with I, j, and k, making sure that we have the appropriate plus minus plus pattern here for that determinant. And we'll calculate one component at a time, partial derivative of natural log x plus z with respect to y, partial derivative xy squared with respect to z. Well, both of those are 0. And then we'll continue along and calculate the y component and calculate the z component. And if we simplify that, we end up with curl of f being the vector function 0, negative 1 over x, y squared minus x e to the y. Now, here you can see that the curl of f is defined for every value of x, y, z except for x equals 0. But because our initial function was only defined over the region for x greater than 0, it wouldn't make any sense to calculate the curl for negative values of x. So we're going to restrict curl f to also just be for values of x greater than 0. Now, what about the divergence of f? This is the dot product of nabla and f. So we are going to be looking at taking the partial derivatives of each component. We will take the partial derivative of x e to the y with respect to x. We will take the partial derivative of xy squared with respect to y. And we'll take the partial derivative of the natural logarithm of x plus z with respect to z. That gives us e to the y plus 2xy plus 1. And remember that this is a scalar valued function, so there is no components, no commas, or no triangular brackets. This is simply just the addition of functions. And even though this looks like a nice continuous function for the divergence of f, we have to restrict the domain. We have to restrict the domain to x greater than 0. All right, well now we know how to compute these 4 different derivative type of objects. We've got the gradient, curl, divergence, and the Laplacian. Now, there's going to be a lot more theory that we can take a look at with these 4 objects, but really for this video, it's good to know how to calculate that and hopefully have an idea of the interpretation. But I'm going to end this video with a little bit of a strange, maybe almost paradox. An example of a couple fields, just even in 2 dimensions, so they're easy to visualize, where you would expect to be able to interpret curl and divergence easily, but it's not exactly what you expect. Here I've got 2 fields. I'm calling them E instead of F, and there might be a reason for that. E xy is simply just the vector field defined by x, y, all scaled by dividing by x squared plus y squared. And I've got another vector field E, which is simply negative y, x, but all being multiplied by the scalar 1 over x squared plus y squared again. Well, these are very similar to the examples we looked at earlier to kind of understand curl and divergence, but let's actually calculate them in both of these scenarios. This first vector field E, the red one here on the left, it certainly looks like it is diverging. We would expect a positive divergence, although you can see we can't calculate the divergence at the origin when x and y are both equal to 0. But let's calculate it. Remember, the divergence here is where we have the dot product of our vector differential operator and E. Applying the differential operator to each component, we'll have a quotient rule on the x component plus the quotient rule on the y component. Combining this over a common denominator and adding like terms, we can actually see that the divergence of this field is equal to 0. Now that is super counterintuitive because it definitely appears that all of these velocity vectors of the fluid are pointing outward from the origin. But here you can see this little region highlighted here. Imagine that we're looking at this volume and we're looking at the mass flowing in and flowing out. Well, if we're taking the mass flowing in, you can see we have high velocity flowing in and lots of low velocity flowing out. There's very little of this high velocity fluid flowing in because that is close to the origin. But as we travel away from the origin, there is going to be lots of slow fluid flowing out. And as a result, you can imagine this as fluid flow going from a narrow opening to a wider opening. It doesn't have to travel quite as fast out of a wide opening as a narrow opening. It's like a little bit of a pipe. A very narrow opening would have a lot of pressure going in, but if we're not compressing the fluid, we have a wide opening on the other side, it doesn't need to be flowing quickly. There would be no compression happening here. It is incompressible. The divergence is equal to 0. So not intuitive by any means, but you can calculate it and see that that is true. Now over here in this blue example, I'm using E again, maybe there's a reason for that. Here it definitely seems that we have circulation of this fluid in a circular motion, and it appears to be counterclockwise. So we would expect our curl to be positive in the z-axis pointing out of the page. But let's actually try calculating it. Now remember, if you want to use the cross product form for calculating curl, but you have a two-dimensional vector field, simply just let its z component equal 0. And this will result in having our x and y components both equal to 0 for curl. And we simply need to calculate the z component, partial derivative of x over x squared plus y squared with respect to x, minus the partial derivative of negative y over x squared plus y squared with respect to y. I'll leave that as an exercise for you. And again, you'll have to use more of these quotient rules and add them together, and you should also see that this equals 0. And that is, again, counterintuitive because we obviously see this counterclockwise circulation. But we're really thinking about circulation at a single point, not necessarily as a whole here. Pick a point. We can pick a point in this region here, and imagine that we have this little spinner in our fluid. It's like little paddles, and we're trying to figure out which way it's going to turn. Well, now you're thinking about fluid pushing on the paddle on the inside here, being very, very quick, and fluid on the outside of this paddle being very, very slow. So in terms of thinking about pressure, we have lots of pressure on this. We have lots of little pressure fluid on this side. There's not a lot of this high pressure fluid pushing on this side, and there's a lot of low pressure fluid pushing on the other side. And as a result, it doesn't cause any sort of rotation. Our curl is equal to 0. So these are kind of two paradoxical examples where your intuition falls apart a little bit. It's much easier when we have higher velocity fluid further away from the origin, and then it becomes a little bit more obvious. Well, purpose of this video, just to hopefully explain the concepts of these four differential kind of objects. We've got the gradient, we've got curl, we've got divergence and Laplacian. Now remember, curl and divergence act on vector valued functions, whereas the gradient and Laplacian act on scalar valued functions. But they are all putting this nabla, this vector differential operator, to use in some form of multiplication. So know your difference between those different operations, which one gets you what kind of output, whether it produces a scalar or a vector. And also, most of the time, your intuition on curl and divergence kind of holds true. You can think about whether you're diverging away, it's like a source, and you're getting less mass in a volume. Convergence being the opposite, where it's actually compressing together. And curl being the circulation around that curl axis given by the right-hand rule, with the magnitude of curl kind of giving you an idea of how fast this fluid is rotating around that axis. Well, we'll look at some more theories and implications of that in the future. So thanks for watching, and I'll see you in the next video.